Hi everyone, welcome to this week's online carbon inference seminar. Today we're going to host a young researcher seminar. Two speakers will be presenting today without a discussion. So our first speaker is Abhin Shah from MIT, who will be talking about on counterfactual inference with unobserved confounding via exponential family. And the second speaker will be Brian Gilbert from NYU, and who will be talking about identification and estimation of mediational effects of longitudinal modified treatment policies. And for Brian's talk in Q&A, there will be his collaborators, Kara Rudolph and Nicholas Williams from Columbia University. And today's Q&A will be handled by Georgia. And Georgia, please go ahead to introduce this a bit.
Thanks, Ying. Hello, everyone. If you have questions during the talks, please submit them as soon as you have them through the Q&A. Since we have two speakers today, we will let them go through their talks, but hopefully we will have time at the end of each talk and at the end of the seminar for your questions to be brought up to the speakers. Like Ying said, Brian has collaborators in Q&A to help with questions as they arise. All right, so thank you very much. And Abhin, I think we're ready for your talk.
Yes. Okay. Hi, everyone. Thank you for the introduction. I'm very excited to tell you about a new framework for counterfactual inference, despite the presence of unobserved confounding using exponential family. This is joint work with Raz, who is a professor at Cornell Tech, and Devavrat and Greg, who are my advisors at MIT. In this talk, we are going to exploit high-dimensional actions and outcomes for personalized causal inference. I'll elaborate more as we proceed. Okay. As a motivating example, let me walk you through a sequential counterfactual question in the context of mobile health. Mobile health is a personalized healthcare technology that is gaining prominence lately and likely would be the way we bring healthcare solutions to individuals. Companies like Apple and Fitbit use smartwatches to collect massive amounts of observational data. For example, these companies record the exercise routine of individuals, say over a period of capital T days. Every day, the smartwatch records the exercise performed and the amount of calories burned by an individual. In other words, the exercise sequence is the action of interest, and the corresponding calories burned is the outcome of interest. Okay, and I'm going to denote this action and outcome by A and Y respectively. One of the goals of these companies is to provide personalized, accessible care to the users. For example, there is a growing demand to build systems that recommend a personalized workout routine so as to, say, maximize the expected calories burned by the individual. Okay, the individual exercise choices and the corresponding calories burned are influenced by many factors. For example, stress level, diet, sleep quality, or say heart rate. And it turns out that some of these factors, such as stress level and diet, are not recorded directly by today's smartwatch, and hence they could potentially act as unobserved confounders. And let us denote such unobserved confounders by Z. Note that these variables could also potentially vary over time, which I will touch upon in a bit. A key question that needs to be addressed is as follows. What would have happened to this individual's calories burnt if they were to undergo a different sequence of exercise routine while keeping the confounder fixed, or while keeping their stress level and diet unchanged? This is a counterfactual question where the actions and the outcomes have become high dimensional. As a result, the number of action configurations scale exponentially with capital T. And therefore, running experiments or, say, performing randomized trials becomes infeasible. So the key question of interest here is, can we perform such personalized causal inference from observational data? It turns out we can in many scenarios by using the power of repeated measurements. So for simplicity, assume that only the stress level acts as the confounder and consider two simple scenarios. In the first, the stress level is fixed over time, say it's always high. In the second, the stress level is varying with time, say it's high with probability, let's say half, or low with probability half, okay? And I'm representing the binary value of stress using coins in the slide. So if you only have one measurement, then statistically speaking, it is not easy to distinguish between the two scenarios. But if you have repeated measurements, then you can actually distinguish between the top sequence and the bottom sequence. In fact, the more measurements you have, the easier it becomes. In other words, the point here is even if the confounders are unobserved, but have some structure to it, it can be exploited with repeated measurements or in high dimensions. Unfortunately, reality is not as simple as this toy example. And in this talk, I'm going to explain or formalize some of the intuition on this slide. In particular, I'll provide you an algorithm to perform personalized causal inference as long as the amount of variation in the confounders is appropriately controlled. Okay. And more generally, I'm going to rely on the richness of modern observational data. Due to digitization and pervasive sensors, we're collecting data at an exponentially increasing pace. Having repeated measurements is just one dimension in which today's data is rich. Companies like Apple and Fitbit collect such smartwatch data from many individuals, say capital N. Our hope is to extract information from such data by observing that oftentimes individuals behave in a similar fashion. Finally, we also want to draw power from auxiliary information recorded by the smartwatch, such as sleep quality or heart rate. Okay. With that, let me state the key takeaways of this talk. To enable individual level counterfactual inference, on the right-hand side, we introduce a new framework using exponential family. Exponential family is the most generic class of parametric distributions out there. Here are some examples of distribution in this family. These distributions show up everywhere, provide the right model for a variety of settings, and have many desirable properties. A particular way of writing the distribution is as I have over here, where x is the random variable of interest and theta is the parameter that is parameterizing the distribution. The expressiveness of the distribution depends on the choice of the function g, known as sufficient statistics. For example, if the distribution of interest were the Gaussian distribution, then theta would capture the mean and the covariance, and g would capture the linear and the quadratic interactive terms. One of the key tasks in the literature on exponential family is to learn the distribution, that is the parameter theta, given many samples for a specific choice of g. Okay. And over the last century, perhaps the most popular method of doing so is the principle of maximum likelihood estimation. This procedure has excellent statistical properties, but it has some computational concerns. In a series of works, we have come up with a computationally efficient alternative to learn the parameter theta. While this, as is a great insight, it does not help us solve the problem on the right-hand side. So what we have done is, building on these insights, we have come up with a way to learn many different exponential family distributions while having access to a single sample per distribution. And this is what enables individual level counterfactual inference. Okay, so let me now explain how to model the counterfactuals using exponential family. Graphically, the observational world and the counterfactual world are closely connected. The counterfactual world is obtained by removing all the incoming arrows of the action, setting its value to the alternative, say A tilde, and then trying to understand its effect on the outcome, again, while keeping the confounders fixed. Our key insight is that the conditional distribution of the outcome, given the action and the confounder, remains invariant across these two worlds. That is, the way the calorie count behaves given the choice of exercise and the stress level remains invariant or identical. That is because if you look at these two graphs, the only change happens in how the action is generated. But given those, the outcome generation remains the same. Therefore, we model this conditional distribution as a generic exponential family and learn the relevant parameters. I will illustrate this using a simple example, and I'm happy to talk about the general setup during Q&A. In this simple setup, let us use these two parameters to capture the various interactions. So I'm using phi zy to capture the interaction between the confounder z and the outcome y. And I'm using phi ay to capture the interaction between the action A and the outcome y. Then one of the simplest possible forms of the conditional distribution is as I have over here. So the distribution is proportional to exponential of a bilinear term, which is capturing the interaction between A and Y via the parameter phi ay, and likewise for between Z and Y. Then the counterfactual distribution is obtained by simply transporting the parameters from left to right, and the form of the distribution remains invariant. So you simply learn these parameters of interest, plug in the new value of A tilde. But the difficulty here is that Z is potentially unobserved. So let us focus on this counterfactual distribution and bring back the n individuals we had from before. So the confounder value, the value of Z, could potentially be different across all of these n individuals. So as a result, we have n different distributions that we need to learn while having access to only a single sample per distribution. So as posed, this question is challenging as we do not observe the confounders. So how do we solve this? Well, we note that there is some structure across these distributions. First, the parameter phi ay is actually shared by all of the n distributions. However, the term zi times phi zy is actually going to be different for all the n distributions. So an equivalent learning task is to learn these n+1 parameters, where the first parameter is shared by all the n individuals, and the remaining n parameters, each one of the parameter is specific to given individual. Okay. In other words, what we have done so far is we have parameterized the counterfactual distributions for this n individuals of interest by two kinds of parameters. The first, which is shared by all the n individuals, and the second, which is specific to each given individual. So if the confounders were actually observed, then our task would have been to learn the parameter phi ay and phi zy. In other words, we would have to learn a single distribution from n independent samples. And the distribution is of the following form. It turns out that solving this task is not as easy, especially in terms of the computation associated with it. So let us take a small detour and understand how to solve the problem on the left-hand side in a computationally efficient manner, and then we'll come back and address the problem on the right-hand side. So we start this detour by noting that the distribution in the blue is a special example of the generic family I mentioned earlier. Oops. In particular, now the random vector x captures the outcome y, action A, and the confounder z together. Then the parameters theta can be mapped to phi ay and phi zy, and likewise the sufficient statistics can also be mapped. So for simplicity, I'm going to assume that x comes from a d-dimensional compact space. The denominator over here, v of theta, known as normalization constant or partition function, is simply obtained by integrating out the numerator over the entire support. As I mentioned earlier, the key learning task here is given n independent samples from a distribution p theta star, how do you learn the parameter theta star? If we can do this, then we can perform counterfactual inference when the confounding is observed. Let me quickly go over one example. Consider the one-dimensional Bernoulli distribution where the sufficient statistics G is simply equal to x. And the parameter theta has a one-to-one mapping to the expected value of the random variable. Now, if you were to give me n independent samples from this distribution, what I would do is I would compute the sample mean and plug it in this equation to get an estimate of the value theta. So this procedure, more generally, is known as maximum likelihood estimation. A convenient way of interpreting MLE is that it minimizes a KL divergence. In particular, it minimizes the KL divergence between the true distribution P theta star and the reference distribution P theta. Further, under some minimal regularity conditions, theta MLE will be equal to theta star. Now, if you open up the KL divergence, the resulting expression looks as follows, where you have an expectation in the first term and the log of the partition function over the second term. Now, if you were to give me n samples, what we would do is replace this expectation with an empirical average, and this is the form of maximum likelihood estimation that we are most familiar with. In other words, here I'm simply minimizing the negative log likelihood. For any estimator, we are interested in its statistical properties as well as its computational properties. MLE has excellent statistical properties. In particular, the 2 norm of the error scales as 1 over square root n, which is the best one could hope for in a parametric problem like this. While this is great, computing this estimate becomes intractable as it involves computing this high dimensional integral. In other words, except in a few well-known scenarios, the computational cost of MLE is going to scale exponentially with the dimension d. In other words, it is NP hard. Even approximating the partition function up to, say, a multiplicative error is NP hard in general. Okay, so in a series of works, what we have done is we have introduced a new estimator which can be thought of as a computationally efficient alternative to MLE. In particular, our estimator also minimizes a KL divergence. It minimizes the KL divergence between P0 and P theta star minus theta. So you should think of P0 as simply plugging in theta equals to 0 on the distribution, and then there is no dependence on X. So in other words, you are left with the uniform distribution over the support. So essentially what this KL minimization is doing, it is performing a reparameterized MLE or MLE in a reparameterized space or a lifted space. Now, similar to maximum likelihood estimation, under some minimal regularity conditions, theta m defined over here is also equal to theta star. What I really want you to focus on is that magically, after opening up the KL divergence, the estimator does not depend on the partition function. In fact, it depends on the centered version of sufficient statistics, which I'm denoting by GC. And this GC is often easy to compute, especially when your statistics G has nice functional form, like say polynomials or sinusoidals, as is typically the case. Okay, so to sum up, what our estimator has done is it has taken the numerator over here, and then it has inverted it or added a negative sign inside the exponent, and then centered the statistic. Okay. And note that this loss function is a convex function in theta. So it does not involve any high dimensional integrals. It's a convex function. So it's going to be easy to compute this in polynomial amount of time. Okay, now again, given n samples, what you would do is you would replace the expectation with an empirical average. We show that similar to MLE, the resulting estimate also has excellent statistical properties. In particular, the 2 norm of the error again scales as 1 over square root n, similar to MLE. As I mentioned earlier, the loss function is convex, does not involve partition function, so it is computationally tractable. Okay, so let me finish this detour by giving you the key insight into what happened here. The key object of interest for MLE is the distribution itself, where I have rewritten the partition function, the integral, as an expectation over the uniform distribution. The key object of interest in the proposed loss function is this expression over here, which is equivalent to the term on the right-hand side by simply using the properties of exponent and expectation. What I want you to focus on is the terms that I have highlighted over here. And note that what we have done is we have flipped the order of expectation and exponent in going from left to right, which has converted this intractable integral into a tractable one. Now, this may seem ad hoc, but it turns out that there is an intermediate Bregman divergence matching framework which interpolates the two KL divergence matching frameworks. In other words, there is a class of estimators where one extreme results in MLE and the other extreme results in our method. Okay, so with that, let us go back to the question of counterfactual inference. Remember, we want to understand what would have happened to this individual's calorie count under a different exercise sequence while keeping the confounder's stress level and diet fixed. And so far, we know that the conditional distribution remains invariant across the two worlds. And this was the running example that we are working with. We also know that when confounders are observed, we need to learn a single distribution with n independent samples. And when the confounders are unobserved, we need to learn n different distributions, each with a single sample. Now, let me connect the dots and explain you how to use the new estimator for counterfactual inference. For simplicity, I'm going to assume that the sufficient statistics in the distribution are appropriately centered as required by our loss function. If not, then you can center them without any extra computation cost in many scenarios. Okay, then to apply our estimator, we consider the conditional distribution of the outcome on a given day. Okay, so on day t, the outcome is yt. So let's look at the conditional distribution of that outcome given everything else. It also takes an exponential family functional form where it now depends on the tth row of phi ay and the tth row of phi zy. Okay, then what we do when we observe the confounding is, as before, we take the exponent, we add a negative sign inside it, and perform an empirical average. Now, this is done just for a given day, t. So what we do is we also sum over all the days to jointly learn all the parameters of interest. This is the case when you observe the zi's, okay? Now, what happens is you can actually decompose this loss function into capital T different loss functions. In other words, there was no need for me to combine these all different loss functions together, okay? So we can separately estimate the parameters corresponding to the tiered day by using all the data we have, okay? While this is great, we cannot do the same on the right-hand side where zi's are actually unobserved. So what we do is we reparameterize the underlined term by defining it as phi of I and t, okay? Note that it depends on both the individual I and the day t. So it is this coupling of the two summations that prevents us from decomposing this into separate loss functions as on the left-hand side, okay? In other words, we need to jointly estimate the parameter phi ay and the parameter capital phi. Note that you can think of capital phi it as the effect that the confounder has on the outcome for we show that the loss function is the one on the left-hand side. Also learn the concept is to get parameter phi. Effectively, we have many samples with, but to learn the specific parameter, we essentially only have a single sample per parameter. We need a control certainty that is present in. I'll formalize this using the notion of metric entropy on the next slide. But the key difference between the left and the right is it needs you to establish this. On the left, you can draw bounds from independent samples using something optic inequality. However, the right draw concentration bound dependent samples from coupling. And to enable this, we established log inequalities for exponential family. That led to the key result of our work. So estimating the parameters as in the previous results in an estimate of the distribution. Here, I'm going to provide guarantees mean of the actual distribution. Punchline, S for every individual gets better, data gets richer. Recall, N individuals and capital T was the number of days. Okay, then mean square error is bounded by a term T.
Abhin, sorry to interrupt you. We have some issues hearing you. It's like breaking out. I don't know if there's we could hear you perfectly in the beginning. I don't know if there's any processes going on in the background with the internet.
Okay, let's hello.
I think that this might be better.
Okay. Okay.
And yes, thank you. It seems to be the headphones. And if you can please wrap up in maybe 3 minutes.
Yes.
Thank you.
Yes. Yes. As I was saying, for every individual I, the mean squared error is bounded by a term which looks like m over t whenever n is, say, sufficiently high. Okay. So in other words, whenever you have many individuals and many days, then the mean squared error in estimating the expected counterfactual calorie for every individual is appropriately controlled. So here m captures the complexity or the amount of unknownness in the unobserved confounding. For example, one way to think about m is the number of unobserved confounders. So m over t is controlled as long as the number of unobserved confounders are sparse compared to the number of days that you have. This complexity naturally decreases as you collect more auxiliary information about a given individual. And naturally, m is 0 for randomized trials. So going back to the toy example from before, the complexity is clearly small in situations like scenario 1, because essentially your z is one-dimensional or you only have a single z. In scenarios like scenario 2, when you have many days, the complexity can still be controlled when there is a strong correlation across the value of, say, stress level or many different days. And our result captures this dependence of the complexity by using the notion of metric entropy. So our work also opens new venues for the literature on panel data. Panel data is the data of many individuals collected over many time periods. So let AT denote the exercise performed in our context on day T, and YT be the calorie count on day T. In the data collected by smartwatches, we expect the exercise today to cause exercise tomorrow or have some sort of a causal relationship. However, the existing literature does not allow for the sequential dependence between the action and the outcome. They only allow for correlations through the confounders. By contrast, our work allows for direct sequential dependence of many natures across the action and the outcome across days. So with that, let me end by restating the key takeaways. So on the counterfactual side, this work opens new possibilities by answering individual level questions when you have sequential dependence between the actions and the outcomes. And to enable this, we introduce a new framework using exponential family modeling. At the heart of this framework lies this loss function, which is computationally and statistically efficient, and also lets you learn many different distributions, each with a single sample. Happy to answer any quick questions.
Thank you, Abhin, for the great talk. We have one question in the Q&A. Probably we can quickly do that and move on to the second talk.
Sure.
So the question is, could this alternative to MLE work also for other estimation approaches, such as method of moments?
I see. So, so the answer is, so far, what we understand is that this loss function It works when the underlying distribution is exponential family. But if you have, let's say, a mixture of exponential families, then it's unclear if the loss function works or doesn't work. So that is something that we haven't yet addressed. But as long as you have a distribution belonging to this family, then you can think of this as an alternative to MLE.
Thank you. And we still have more questions, but due to the interest of time, we can leave it to the end, or I'll forward it to you later.
Sure.
So Brian, please feel free to get started.
Hi, everyone. 1 second.